In Part 4 of Lecture 9, we discuss allocating frames. How many frames should a process get? If it's a single-user system, the answer is quite simple. All of them, excluding the ones that the operating system needs. But if the system is multitasking, it's more complicated. First, we need to address two important questions. How many frames must each process have? We know that there is an actual minimum number of frames. We'll take another look at that in a moment. We also need to know if frame allocation is global, from a system-wide pool of available frames, or local, from a pool of frames available only to this process. Every process needs at least enough frames to complete an instruction. In the case of the VAX, this could be as many as 7 pages, with 1 for the instruction and 2 each for all 3 operands. We need 2 pages to allow for indirect addressing. In either case, that still requires a lot of pages. At first, assigning the same number of frames to each process seems fair. So if we have I frames and n processes, giving each process I over n frames seems fair. But it really isn't. A small process may have enough frames for all its pages, and a large program with large arrays and a lot of code may not have enough frames to hold a significant portion of the program. A fair way is to give each process in accordance with its needs. If a process with a total memory requirement of 100 megabytes is fighting for 20 megabytes of physical memory, a process needing 15 megabytes should be allotted enough frames to hold 3 megabytes. This is proportional to its needs, and it is fair. Once a computer system is designed to multitask, the operating system's designer must decide between local and global allocation, whether each process will have its own allotment of frames, or whether a process can take frames from one large allotment of available frames that is shared by all the processes. Both of these have advantages and disadvantages, as we will see in a moment. Local allocation means that the process has an allotment of frames, and if a new page is needed, it must be loaded into a frame belonging to that process. If all of a process's frames are in use, one of those pages will have to be replaced. Generally, the number of frames that a process has won't change. This means that a process can't get extra frames, but it can't lose any either. A process is not dependent on the behavior of other processes to determine how many frames it has. However, this can backfire because other used frames of other processes are not available. With a global allocation algorithm, a process can replace a page from a set of frames that have been allocated to all user processes. Processes with a higher priority or a greater need can increase their allocation at the expense of lower priority, less needy processes. The end result is that the frames can be used more efficiently. This efficiency translates into greater throughput for the system. Thrashing is a phenomenon where a system spends far too much of its time swapping pages and not enough of it completing the useful work. As you see in the illustration, increasing the number of concurrent processes increases the utilization of the CPU until you reach some point, and it drops off precipitously. What happened? In systems with global page allocation algorithms, you reach a point where the process suddenly needs a large number of new pages, and these are placed in frames that used to belong to other processes. Now, these processes increase their page fault rate as they need the frames that were taken from them. After a while, the processes spend more time trying to grab frames back from each other and far less of it doing their real work. How can we stop thrashing? The easiest way is to cut the degree of multi-programming. This may mean suspending processes until some of the others have been completed, but it can help restore the system to its normal operations. How can we prevent thrashing? A local replacement algorithm can limit the effect of an overly high page fault rate to just one process. Or better yet, we can develop a method for ensuring that each process gets the right number of frames.